Okay. Good afternoon, everyone, and thank you again for joining me this afternoon. Um, um, you may be wondering, no, why I chose this topic. Um, Measures of central tendency and uh, dispersion are actually very common, no, topics in statistics. But I want to show you how I teach it to my class, no. So it's not just talking about the mean and the standard deviation as standalone alone concepts, but rather how they come together, no, measures of central tendency and dispersion to make sense about a data set. Okay, so the worst thing you can do when you present a data set is just show all the numbers. So imagine you show what you show raw data, let's say 100 numbers of how, let's say, the exam scores of students, and there's no order. No, you just show the raw data. Okay, when you flash that on the screen, uh, in a maybe in a second or two, people will be able to see what the highest or the lowest score is, but that's it. Okay, uh, to be able to make sense of the data, no, it is always measures of central tendency and dispersion can be applied, no, and it right away when you're given a measure of central tendency, whatever it is, or a measure of dispersion, right away you have some sense of how the data set is. Okay, so let's start. Let me share. No. Oh, by the way, today I'm not going to be using PowerPoint. No, I'll be using. I will be writing on paper, so I have a camera that focuses on my sheet of paper, so that you can follow me in some of the computation. So I hope this works better for you. Okay, so let's start.
Yes.
Okay, so when you talk about measures of central tendency, this is a typical value, no, for a given set. You want to know what value that is that the other values tend to center around. Okay, that is what you mean, no, by a measure of central tendency. And there are three measures of central tendency, and I'm sure all of you are familiar with this: the mean, the median, and the mode. Okay, now this is my first question to you. Which of these are averages? So the answers I'm getting are all mean. Okay. Okay. So actually, ladies and gentlemen, all of these are averages. Okay. Strictly speaking, very good. Okay, someone said all. Strictly speaking, the mean, the median, and the mode are all averages. It is just that we have gotten so used to thinking of the mean. When we say, oh, get the average of the weights of the students in this class, right away what comes to mind is get the mean. No, but actually all of these are averages. No? Okay. Okay, next. So let's start with the first, the mean. Okay, the mean is most frequently used. Okay, and it is a good measure in the sense that it takes into account all the values of the data set, no, all the data points. But remember, never use the mean when there are extreme values in the data set. And I am going to illustrate this with this example. Okay. Let us say you are um, a statistician and you work for the Philippine Statistics Authority, the PSA. And you want and your task, no, by the government to go around the country and make a list of all the villages that will be needing ayuda from the government, no, in the sense that they don't earn enough for their families. Okay, so As a statistician, you travel, no, and then you find this fishing village. No, in this fishing village, there are 5 houses, and these are the monthly uh, incomes, no, of these 5 houses. So this house here earns 3,000 a month. This earns 2,000. Don't mind this red house first, no, don't mind this. So in this fishing village, you see these 5 houses, and the figures beside the houses are what, or below the houses, are what the households earn a month. Okay. Even without, I'm sure you know, as I know, that earning 3,000 or 2,500 a month is very small. No, even for a fishing village, no, that is very small. So you get the average, no, and you get the mean, and you find out that after adding all of these 5 and dividing by 5, you get a mean of 2006. Okay, so you will report to the government that this particular fishing village would need help, no, from the government, because it's a poor fishing village, because on the average, as measured by the mean, they only earn on the average, each household, no, earns on the average 2,600 a month, and that is very small. Now, what happens if a very rich person finds this fishing village so beautiful and decides to set base here? Okay, now this particular house, no, of this very rich person, he earns 1 million a month. Okay, so if you include the 1 million, no, in the data set and compute for the new mean, this will now be 1 million plus the sum of these 5 houses, 13,000 over 6, no, and this is approximately okay, let's check, no, so that's 1,013,000 plus 13,000 divided by 6, and that gives you approximately 169,000. Okay. Okay. Now, if you're the statistician, no, and you get the mean of this fishing village, and you say, oh, on the average, a household earns 169,000, you will of course not report this anymore to the government, diba? You will not say, oh, this fishing village needs help from the government. Of course not, because 169,000 household income is high. No, I mean, even in Metro Manila standards, actually the government says, no, that for Metro Manila, this was 2 years ago, no, if you're earning like 16,000 a month for a family of 5, you're already above the poverty level. So can you imagine if you earn 169,000? No, that's already very high. So you will make a mistake and not report that this fishing village needs help just because of one house that had a very high income. Okay, and that is the drawback of the mean. Never use the mean when you have extreme data points, because it will totally make your conclusions wrong. Okay, like in this case. In this case, you will say, oh, each household earns an average of 169,000. No, they're pala are okay subdivision. In fact, middle income or even upper middle income. No, in fact, it's wrong. No, 5 households are very poor, and only one household is rich. Okay, so what is a good thing about the mean? No, the mean always exists and is always unique. And we will find out in a while that that is not true for all measures of central tendency. Okay, now let's move on to the median. So the question is, so what will you use if there are extreme values? Okay, if there are extreme values, you must use the median. Why? Because the median is what is called a positional measure. If you have a database, no, let's say these are your data, and even if you have an extreme data here, no, all the rest are like clustered here. The median, since it is a positional measure, would be that value that divides this data set into two equal parts. Okay, so we know that the first thing you need to do is to sort this, no, from lowest to highest. And if it is, like in this case, 7 data points, then you just have to get that in the middle, which is this. Okay, so you can see that the median is not affected by this. So if this happens to be the household that earns $1 million a month, the median is totally not affected by that. Okay, and you can see, no, that 50% earn above the median and 50% earn below the median. Okay, now the last meeting, I'm very sorry, no, but there was one question that was posed, and I unfortunately I answered it incorrectly. No, and I only realized it after the session was over, and I was really hoping, no, uh, for this day to come where I could rectify my answer. Okay, so for the one who asked, can the median be used for ordinal data? The answer is yes. Okay, because ordinal data is just data that has some kind of low to high scale. Okay, so you can use the median, okay, when you have ordinal data. And as I mentioned in the previous lecture, that while Likert scales, okay, are theoretically ordinal numbers, social scientists have relaxed the rules and consider them uh, interval. Okay, so you can even get the mean, no, for Likert scales. So for the one who asked that question, I'm very sorry. Yes, for ordinal data, you can use the interquartile range. I think you also asked that question, and yes, you can use the median. Okay, so again, like the mean, the median always exists and is always unique. So what are examples of using the median? Okay, like for example, when you want to get the average income of a country, and it doesn't necessarily have to be a poor country like ours, no? Even the United States is, in terms of, when you think of the distribution that represents, no, the income in the United States, it is still skewed, no? It is still positively skewed. So what do you do, no, when you have a distribution that looks like this, no, where there are many who earn a certain amount, no, but there are some who are like very, very rich? You use the median and not the mean. Okay. Okay. Now let's go to the mode, which is the third measure of central tendency. Okay. So the mode. Okay. Take note of this. No, the mode can be used when data are measured in a nominal scale. Okay. So we know that in a nominal scale, um, the values of the variable are all equivalent. So like if I ask you, what is your favorite? No, sorry. Let's say what dish, no, did you have for lunch, and then you answer, let's say Japanese or Italian or Filipino or Chinese, no, the only relationship they have is equivalence. Okay, now note that the mode, okay, is the only measure that can be used for qualitative data. Okay, so you can even talk about what is the average sport that is played in your school. Okay, so pwedeng mode. How does that work? You just have to get the number of students, no, who play the sport, no, that is played by the most number of students. So like let's say 15 play basketball, no, in your school, and then 2 play volleyball, and let's say 3 plays let's say futsal, around what value does the, or around what answer does the data, around what answer does the data center around? It's basketball. Okay, so you can talk of like an average, in quotation marks, for qualitative data. Other examples are, what is the most like scent of this shampoo? Okay, again, the mode is the only measure, of central tendency that can answer that question. Or like this, let's say you make shoes. Now you're like, what what which measure of central tendency can help me so that I know what size to make more of? Okay, you will not choose the average, no, because for all you know, if you choose the average, no one will fit into those shoes, no. But it is the mode that you should use for a question like this. Now, we know that it's very clear, no? Let's say our data are as follows: 1, 2, 2, 3. What is the mode here in this data set? 2. Very good. Okay. What if it's 1, 1, 2, 2, 3? Good. 1 and 2. And that is what you call bimodal. And a bimodal distribution looks like this, no? There are 2 peaks. Okay, now, how about this one? Dear participants, what if the numbers are 1, 1, 2, 2, 3, 3? What is the mode? Okay, very good. For those who answered, no? This is the correct answer. There's no mode. Okay? This is the answer to this. Why? Because you can see all of them appear with the same frequency. Now, I have some students, no, when I ask them this question, they say 1, 2, 3. No, that's not the case. Okay? Because 1, 1 occurs 2 times, 2, 2 occurs 2 times, 3, 3 occurs 2 times. So all the same frequency, so there is no mode. But if I add the number 4, no, then the mode is 1. The modes are 1, 2, and 3. And that is trimodal, okay? Or that is trimodal, okay? So note that, no, the mode may or may not exist in the case of no mode, or but in the case if it's unimodal, no, or bimodal, it exists. Now, if it exists, it may or may not be unique. Okay, it may or may not be unique. So, comparing this to the mean, no, and the median and the median always exist and are always unique. The mode, on the other hand, may not exist, no? Like in the case of 1, 1, 2, 2, 3, 3, there is no mode. And if it does exist, it may not be unique, like if it is bimodal or trimodal. Okay. So the rule is, if you have 3 or more modes, okay, do not use the mode as a measure of central tendency, because a measure of central tendency helps your audience, no, determine the value around which the data center. Now, how can you have an idea of that value around which the data center if you're giving too many answers, no? So, for example, the let's say if you go to this particular European country, you will what is the measure of central tendon, let's say, or what is the value, what is the height value around which the data center, no, you cannot say 5, 2, 5, 4, and 5, 6, diba? The one you're talking to will not get a clear picture of what value that is around which the data center. Okay, so if you have more than three or more modes, okay, use another measure of central tendency, like the mean or the median. Okay. And again, the mode is the only measure of central tendency that can be used for qualitative data. Okay. Now, the only measure of dispersion I'm gonna discuss with you is the standard deviation. Okay, because this is what all my subsequent examples will be on the standard deviation and the mean. Okay. Uh, Um, so what is the standard deviation? Okay. The standard deviation is given by this formula. It is the square root of the summation of xi minus x bar open close quantity squared over n minus 1. Okay. Now, as you can see, each of the values, the mean is subtracted from each of the values. So the standard deviation is the scatter, around the mean. And the advantage of the standard deviation versus the range, for example, is that all values in a data set are considered when you solve for the standard deviation. Okay? Unlike the range, when you get the range of a data set, it is only the maximum minus the minimum value. It doesn't care about any of the values in the middle. Okay? But the standard deviation, on the other hand, considers all the data points. Now, this is how it is defined, in textbooks. But when I solve, for the standard deviation, I would rather use this computational formula. Now, it is easier for me, especially if you have a huge set of data. You want to compute the standard deviation for. Okay, now I have another question to the participants. Can the standard deviation be negative? No. Okay, very good. No. Okay. My students, when I ask this question, they say because you cannot have a negative under that square root sign. Okay, but rather you cannot have a negative answer, no? But actually, that's not the real answer. The real answer is because standard deviation measures dispersion. It measures scatter from the mean. So there is no way that you can get negative scatter or negative dispersion from the mean. Okay, that's the answer. Now, my second question about the standard deviation is, can it ever be zero? Can a standard deviation be zero? Or should it only be positive? Okay. The answer is it can be zero. Okay? How does that happen? If you have something that looks like this. Yeah, someone answered correctly. If there is no dispersion. So if you have numbers like this, so the mean is 5, and the standard deviation would be the square root of the summation of each of these numbers minus 5 squared over 5 minus 1. This one is, of course, 0. So a standard deviation can be 0 if if all the elements in the data set are the same. Or it can be positive, but it can never be negative. Okay, because it is scattered from the mean. Okay, now, how do now, okay, I said no, when you discuss measures of central tendency and measures of dispersion, always find a way to make them relevant. Why should they always come together? You can never talk about data without one or the other. And this is my example there. These are some of my examples. Let's look at number 4 first. I always joke my students about this question in number 4. Okay. let's say my students are 19 years old, no? Let's say they're second year college. And I ask, um, sige, I will introduce to you, uh, let's say, three men, because she said she wants someone not far from her age, but older, no? Basta all I can tell you is the mean of the ages of the ones I'm going to introduce to you are 20, is 20. That's all I'll say. I'm not going to talk about the standard deviation, just the mean. Okay? And she'll say, okay, 20 is a good average age. Introduce the three to me. And I will introduce to them these three people. One who is 5, one who is 15, and one who is 40. A very young boy, a teenager, and a mature man. The mean of this is 20. Okay, but would she want to date any of this people? I don't think so. No, because what they were hoping for was someone who was like 21, 22. Okay, this is a very, it is like a funny example, but it's true. No, if you don't care about the dispersion, and then you can end up with a case like this. No, now I could also introduce her to someone, three people who are age 19, 20, and 21, and the average of these three is 20. Okay, but of course this is a better group, no, to introduce to my student rather than someone like this. But you will not know which group I'm going to introduce to you unless you ask me what is the dispersion of the data. No, so the more correct way was to ask, if I told my student I'm going to introduce you to three male, the next question should have been, but ma'am, what is the dispersion? Diba? Diba? She said, I don't like the dispersion to be too big, like this. She could have told me that the dispersion should be very, very, very small, like this. Okay. Now, another example. Okay. Another example. Let's say I ask you, I will have you teach, you can choose between these two classes to teach, class A or class B. Basta I'll tell you, the IQ of both classes of the students, no, is 110. Now, if you were a teacher, if I were a teacher, no, and the principal said, "Oh, Leia, you choose between these two classes," basta their average IQ is 110, both classes. No, I will not decide just based on a measure of central tendency. No, I will say no. What's the dispersion? Tell me. Then I will choose. Okay, why? Because in my 20 years of teaching, I have handled classes which look like this. The IQ ranges from 90 to almost genius. Okay? The IQ of a genius is 160. Okay. Can you imagine teaching a class like this? Co-teachers. This is a very, very hard class to teach. Okay, and I have had a class like that several times. Why? You teach a subject matter, these ones, no, with IQ close to this, no, first of all, the ones, the almost geniuses, no, they get it right away, the lesson, no. But these ones here, you might need to answer, you might have to repeat the second time. Now, these ones may understand it already. These ones may understand it now after the second time. I mean, for sure they do. But this one, you will need to repeat a third time, a fourth time. And what happens? These ones are already talking. They're not listening to you anymore because they know it. So they're making noise in class. While these ones are still struggling to understand the lesson. Whereas, sabi ni Howell, extreme masyado. No, you know what? That's not extreme. In one of the schools I used to teach, one of my students was the number 4th best in math in Asia. No, he was like this, if not even more. In fact, before I even entered that class, now the chair of the department warned me. She told me, Leah, one of your students is the number 4 best in Asia, no, in math. So I was like, oh, well, of course I was so happy, to have someone very bright in my class. But but this is what happened. No, he could understand so fast and so well, but the others were like, understand. But if you have a class like this, now all of them are just like the same, 115 or 95 or 105. No, if you have what you call a homogeneous class, this class is much easier to teach than this one. Okay. Now, another reason why the two must come hand in hand, and I also always, in my operations management class, I teach this example. Let's say you own the company Fruit Loops. You own Fruit Loops, and you happen to be the operations manager, owner and operations manager for this company. Now, when you have an operation like this, producing Fruit Loops, my suggestion is every 6 months you must sample what comes out of the production line to see if what the weight of the boxes still comply to what you promise your customers. Okay, so you say, if you were to look at the cereal boxes, you will see this average net weight 16 ounces. Average net weight 16 ounces. Okay, if you look at cereal boxes, you will see that. So I'm the operations manager, and in 2017, I got a sample of boxes, and so how do you sample? I could sample like every hour for 12 hours in a day and get, let's say, 9 boxes every hour, and then get their weight. So if I get the weight of all those boxes, I get 16, as I promised. A year later, I do the same procedure. I get 16. 2 years later, I get 16. So I go to management and say, walang problema sa operations natin. There is no problem in our operations. Really? Really? Okay? You're only looking at the mean. You're not looking at the dispersion. But this is pala what is happening, and you're not even aware of it. In year 2017, your box, the standard deviation was 1 ounce. They were ranging from 15 to 17 ounces. Okay? In 2018, they were ranging from 14 to 18. And in 2019, they were ranging from 13. And you're more in trouble in 2019. But if you just report the mean, you're saying, the mean has not changed. Okay? So what happens here? In this situation, the boxes now are very light. So when you shake the box, in fact, my students do that. When they buy potato chips or cereals, they shake the box before they buy, and they notice that the box contains less just from the sound. And then, so this one, your customers will not like it, that they're paying the same price but getting less in return. Here, of course, the customers are happy because there is 3 ounce more in a box, of cereal, but you're losing. You computed your profits such that only the average should be 16, but now you're putting 19, as much as 19 in a box, and that's not good for your company. Now, what if, on the other hand, all you're reporting is the dispersion? Okay, in 2017, your dispersion was 15 to 17. that is just plus minus 1 standard deviation from the mean. Okay? But look what happens in 2018. Your standard deviation is still plus minus 1. So this is 16 to 18. Okay? And here, if you're here, you will report it is still plus minus 1 from 17 to 19. So what will you tell management? In the last 3 years, our standard deviation has just been plus minus 1 from the mean, so we're okay. But you're not. You're not. Because you're not reporting the changes in the mean. And the mean has been increasing through the years. Okay? So it is not enough to report just one. Again, the measure of central tendency and the measures of dispersion must always go hand in hand. So you do not miss out on anything. Okay? Here, constant mean, but you're missing out on the dispersion getting big. Here, constant deviation from the mean, but you're missing out on the mean getting bigger and bigger. Okay? So both situations are not good. Okay. Now we're all familiar with this curve, no? This is the normal curve. So aside from those examples I gave you, no, for why the mean and the standard deviation are both important, this is another example of why. Okay, when you want to talk about a data set, and that data set happens to be normally distributed, no, you can talk about what is called the empirical rule. Okay, so what does the empirical rule say? Nota, this is a bell shape. It is a symmetrical curve. So what do we know about a symmetrical curve? The mean is equal to the median is equal to the mode. Okay. So what else do we know about this curve? 68%, no, lie between 1 plus minus 1 standard deviation of the mean. Okay. 68% of the data, approximately. Now, not only can you say that 68% lie, so that would be, okay, what is a good example? Let's say age of teachers, no? Let's say the average age of a teacher is in your school is, let's say, 40, with a standard deviation of 3. Okay, so that's 40 here. Plus minus 1 standard deviation is 37 to 43. So you can say that 68% of your teachers have ages between 37 and 43. But not only that, because this is a symmetrical curve where the left, if you split the curve across the mean, the left side is a mirror image of the right side. You can also say this has probability 34% or area of 34%, and this has area of 34% as well. You can say that as well. Okay, so how many of the teachers have ages between 37 and 40? Approximately 34%. Okay, now how about between mu plus minus 2 standard deviations? And then we have 95% of the data, approximately 95% of the data lie between these 2 points. So what ages would those be? So that would be 34 and 46. Okay? So you can say 95%, approximately 95% of teachers in this particular school have ages between 34 and 46. So if there are, let's say, 1,000 teachers in that school, approximately 950 have are aged between 34 and 46. Again, that is not the only thing you can say. You can say that between 34 and the mean, 95% divided by 2, which is 47.5, okay, lie between 34 and 40, and another 47.5 lie between 40 and 46. And finally, within 3 standard deviations, down here, this black line, okay? So you can say that approximately 99.73% of teachers have ages between 31 and 49. Okay, so it's quite a young school. It's quite young, no? If almost everyone in that school is just between ages 31 and 49. Okay, now can you tell me the size of this area here? What is the size of this area? Let us just round this off to 99.7, okay? So it's easier. What is the size of this area? This blue area here. This is the 3 standard deviations, this and this. So I'm talking about this area here. Very good. This is 0.15. Okay, that is 0.15. And what is this one here? It is also 0.15. Okay, why? Because this is a symmetrical curve. Whatever is the area here above the 3 standard deviation mark is also this area here below this 3 standard deviation mark. Okay, 0.15%. Very good. So let us do this example. Okay. So mathematics achievement test scores for 1,000 students were found to have a mean and standard deviation of 500 and 100 respectively. No? If the distribution is bell-shaped, how many of the scores fall in the interval 400 and 600? Okay, that's the normal curve. This is the mean, 500. One standard deviation is 100. And they're asking for 400 to 600. What is the answer? Approximately? For letter A? Very good. Okay, because this is 68% approximately. So 68% times 1,000 is 680. Very good. Now, how about above 700? Here. Okay. Note that the other one here would be 300, right? So if one standard deviation is 100, no? If one standard deviation is 100, so 300, this is already 2 standard deviations, and this one is already 2 standard deviations. So what lies here? Approximately 95%. So what lies here? Very good. Very good. 2.5%. Okay? And where does the other 2.5% lie? Here. Below 300. Okay. Let me ask one last question. How many lie between 600 and 700. This one. Very good. Very good. It is 13.5%. Okay? Why? Because this, from 400 to 600, it's 68%. No? From 300 to 700, it is 95%. So, uh, the difference, no, between 98, 95 and 68, the difference between 95 and 68, no, is 27. So, if I also color this green, this plus this other green area here would be 27%. Okay? But I am only asking for this one. And that is 13.5%. Very good. Okay. So, it's already 4:30. I still have to discuss skewness. Is that okay with the organizers?
Yes, Doc Leah. Yes, Doc Leah.
Okay.
We're until 5:30. So,
Okay.
okay.
Okay. Okay. Now, actually, I wanted to reach up to what we call Chebyshev's theorem because we're talking about the mean and the standard deviation. No, for the normal curve, no, we have the empirical rule, and that is why you're lucky, no, if the data follow a normal curve or a bell-shaped curve, because you can make conclusions like this. But my question is, what kind of conclusions can you reach if it's not symmetrical, if it's not bell-shaped? No, and that is where Chebyshev's comes in. But let's see the time, no, because I also want to answer the questions. So, okay, moving on. Sometimes you have curves that look like this, no? And that is what you call a curve that's skewed to the left, no? When the tail is to the left this way, okay, you call that negatively skewed or skewed to the left. Okay, now there are okay, let's start first from this one. Okay, this is the easier curve in the sense that there are more examples that I can discuss with a positively skewed distribution. Okay, so for a positively skewed distribution, what happens? You have something that looks like this. Okay, and I said one example, okay, that follows this kind of curve is income. And I mentioned a while ago that it is not only income of developing countries like ours, but even in the United States, no? This is how the income curve looks like. Okay, so in our case, no, I checked 2016 data, although I don't know if that was the mode, or the mean, the median, or the mode, but let's say it's the mode, no? And it was approximately 25,000, 22,000 actually. No, let's just say that's the mode. And why is it the mode? Because in a y-axis, no, the y-axis is frequency. So you're saying this is let's say number of households, no, who earn that much. So you're saying that many households earn 22,000 a month. Okay, but there are some people, okay, like the Pacquiaos, who else? The Ayalas, the Cs, the Gokong Ways, okay, who earn, this is just a number line, no? To positive infinity. So that there are those who earn like 10 million a month, etc. in this range. So what happened? What happens? The mean, okay, which is always pulled in the direction of the extreme values, no? And as I mentioned earlier, the mean, the disadvantage of the mean, it is that it is very much affected by extreme values. And the mean is always pulled in the direction of the extreme values. So the mean would be somewhere here, no? It is pulled in this direction. And let's say this is the mode. Now the median is a positional measure. Okay? So it doesn't care, no, about all the values, as long as, it just cares about what that value is that divides 50% from the other 50%. Okay? So that is a positively skewed distribution. So, and this is how it looks like. Okay? The mean, okay, the mean is greater than the median, is greater than the mode. And there are other examples aside from this. Okay, scores in a difficult exam. Okay, why are scores in a difficult exam positively skewed? In any class, no? Kahit magbigay ka ng mahirap na exam, palaging meron doon mga 1, 2, 3 na ang gagaling, no? They will be able to get high in the exam. So just imagine this is from 0, no, to positive infinity. So if it's a difficult exam, no, many will fail. So let's say out of 100, many will get like 30, no, 20, 30. Let's say the mode just happened to be 30. But there are those na, they're just, aside from being very diligent, they're also very smart. Okay? Like that student I had who was the 4th best in Asia. So that's, 2 of them could even perfect it. And then maybe one of them could, 3 of them, 2 of them got 100, maybe even 3 of them, let's say, got 90. And because of that, no, the mean is pulled this way, no, in the direction of this extreme values. That's why it looks this way. Now, on the other hand, you have a curve that looks like this. Okay, it's negatively skewed. And so again, remember, in a symmetrical distribution, like the normal curve, the mean is equal to the median is equal to the mode. Okay, but not in skewed distributions. So what is an example of a negatively skewed distribution? The opposite of a hard exam, an easy exam. Okay, so what happens if this one is number of students, no? Because it's very easy, majority of them get maybe 90. No? But as teachers, we know this, that even if your exam is so easy, no? And I also cannot understand it. There are still people who will get like 10, no? Or 20. So let's say this is 20. No? Maybe 5 still get 20. 3 still get 10. No? Meron pa nga 0. No? Even if the exam is so easy na nga. Okay, what happens? The mean is pulled in this direction. It is pulled in the direction of the very, very low scores. Okay? That's why, in this case, no? That's the mode. That's the mean. The median, just a positional measure, not affected by extreme values. So in this case, the mean is less than the mode. Okay? So these are just a few rules that could help you make generalizations. Yes, okay. Okay. So we know that skewness, the Pearsonian measure of skewness is x bar minus median over standard deviation. Okay. So again, why do we always want the mean and the standard deviation, at least in this case? Because you can see whether a distribution is skewed or symmetrical. Okay. If a distribution is symmetrical, it is of course skewness is of course zero because the mean and the median are equal. Okay, but when the mean is greater than the median, greater than the mode, or the other way around, no, where we have skewness, you can even we have the following rules. No, when skewness, the value that you compute is less than -1 or greater than 1, you can see that the distribution is highly skewed. When skewness is between -1 to -1/2, or on the other side, 1/2 to 1, no, the positive side, it is moderately skewed. And when skewness is between -1/2 and 1/2, it is approximately symmetric. Okay. And of course, the general rules. No, when skewness is greater than 0, okay, that means when does it become 0? The mean is greater than the median. And when does that happen? When you have a positively skewed distribution like this one. Okay. So when your measure of skewness is positive, you have a distribution that looks like this. When it is negative, you have a distribution that is negatively skewed, like this. The tail is to the left. Okay, because the mean, no, is smaller than the median. Therefore, the measure of skewness will give you a negative answer. And finally, as I said, when mean and median are equal, and that happens when your distribution is bell-shaped, then your measure of skewness is 0. Okay. So let me end here. Maybe I will just discuss the Chebyshev's rule in the next meeting together with hypothesis testing. Okay, so I can answer the questions. Okay, I'll stop sharing.
So the question is, how are the measures of central tendency and measures of dispersion complementary? How are the
Okay.
measures of central tendency
As
and dispersion complementary?
Okay, I gave several examples of that, no, but I think the most striking was my was my was my example in operations management, no. So they're complementary in the sense that giving the answer to only one can mislead the one you're talking to. Okay, it is only when you're able to give the values of both that they have a complete idea of how the database really looks like.
Okay. So let's now move to how many questions do you think you can? There are a lot actually. How many questions do you think you can accommodate, Dr. Leah?
15 minutes.
Okay, so maybe 4 questions. Okay, so let's go to the next question.
Sige,
The next
let's see.
question came from, sige, tingnan natin na, wait and see. So the next question came from June Ward. The question is, when is the best way to use mean, median, and mode to interpret data in a given set? That's very basic.
When should you use? Okay. So as I mentioned, no, in my talk, the advantage of the mean is it takes into account all data points. If there are no extreme values in your data set, use the mean, because the mean will take into account all the points. Okay. But the minute there is an extreme value, shift to the median. Okay. Because the median is a positional measure and greatly affects, no, the average. And the mode, as I said, is the only measure of central tendency that can work for qualitative data or for categorical data. No, there is no way you can compute for the mean for categorical data, because you need except for the Likert scale, no, you need interval data to be able to compute for the mean, because you will be doing uh, addition and subtraction. Uh, Wait a minute, huh? Yeah, yeah. Interval, the you can use the mean starting interval data, but again, for the Likert scale, which is ordinal, the mean is accepted as well.
Okay. So next question actually came from Manolita Ramos Olivo again. Why are mean deviation and standard deviation not calculated using the same average?
Uh, the mean, what does that mean?
Mean deviation and standard deviation not calculated using the same average.
Uh, Wait, sorry, I'm not very familiar with the mean deviation anymore.
Okay.
Uh,
So
oh, okay, okay. I think I can answer that. Wait, oops. Okay. Um, okay. If you notice, no, when you compute for the standard deviation, it is divided by. They're asking for the denominator, no? Why is it not
yes,
divided by the same? By the same, right?
not not calculated using the same average rather.
I'm not, I don't get the question. But if you're asking why the if you're asking why the standard deviation is divided by n minus one and not by n, okay, that is because uh, s squared, no, s squared. Remember, s squared is the sample standard, is the sample variance, okay, and you want it to be a good estimate of the population variance sigma squared, and that only happens when the the sample variance is divided by n minus 1. If it is divided by small n, it underestimates, okay, the population variance. It is only when it is divided by n minus 1 that it becomes closer and it becomes an unbiased estimator of the population variance. Okay, I hope I answered your question.
Okay. So next question, I think we still have time. Next question came from Romer Binamira Brocas, and the question is, do you still need the value of the standard deviation of a set class of scores if what you are determining is the class performance, for example, in a summative test or quarterly assessment, or
Definitely.
we need only the mean and the PL. What is PL? We need only the mean and the PL? Question mark. I am planning
Well,
to
I'm
reform the tool used for this, and on my new tool, SD will not be included.
Oh no, you should always report the standard deviation. Okay? Because as you saw in my earlier examples, even if the mean is passing, no, so you get the impression that you cannot there's no way you can conclude the performance of your class just based on the mean, no. Wait, Garnett?
Yes, yes, yeah, okay.
Your net, can you hear me?
Yes, but you're a bit